Hi everyone. Yes, my name is Sigríður and I will tell you a little bit about Hydrorift. I was a part of an Icelandic group in this project, and as well as Kristján Ágústsson, Aurora Franco and Ólafur G. Flóens, and numerous other people that I have never met. And so the Hydrorift was a cooperation between French and Icelandic scientists, and we are supported by GEORG and the House Orka energy company. The French group was was supported by Geoflux, and the research was focused on a geothermal field in Krýsuvík out on Reykjanes Peninsula. And we put up, well actually they put up, I didn't start on this until they had already collected all the data, but there was a seismic network in operation on the Reykjanes Peninsula from May till October 2009, so for approximately 6 months. So there were 13 stations from the Loki instrument pool and 19 stations that the French group brought, and then we also got data from 8 stations from the Iceland Meteorological Office. And we were they were very lucky that there was an intense seismic swarm that started just 2 days after they had finished installing all the stations. So we had a lot of data with a very good quality. So this is the research area. Krýsuvík is in one of the geothermal fields that we can find on the Reykjanes Peninsula. The Reykjanes Peninsula is an oblique spreading ridge. You can see in the small figure on the inset that the spreading is not perpendicular to the peninsula, which is probably an effect of from the hotspot underneath Vatnajökull. You can see the 32 stations in the small black triangles, and the black diamonds are the meteorological office stations. The small box, you will see it later, that we will focus in on this area. But Krýsuvík is just one of 5 systems out on the peninsula, and 3 of them are being exploited. Out on Reykjanes we have a power plant, and in Svartsengi, which is part of the Grindavík system, and then in Hengill we have Hellisheiði power plant. The reason for the seismic swarm is probably due to an active deformation period in Krýsuvík during this time. Early in 2009, the land started rising. You can see in the top figure, this is a GPS station called Krýsuvík, which is located a little bit south of where the uplift is most. So it's the north component, so when it's going down, the station is actually moving south. And because the station is south of Krýsuvík, we know that the land is rising. And a few months later, it started subsiding and then rising again and then subsiding, and nobody knows what is going on. But we had a lot of seismic activity with this. On the right side, you can see the cumulative number of earthquakes, and we had mainly 3 intense swarms with quieter periods in between. And all in all, we had detected around 10,000 events, which is pretty high for just a few months of research. Around 6,000 or 7,000 of these events were manually viewed by Aurora Franco, one of the French scientists, and then I got all the data from her. And this picture shows 2,800 relocated events. So these are very highly accurate locations of earthquakes. And these are two main areas. To the west, we have Fagradalsfjall, and to the right, we have Krýsuvík, and we will be focusing on Krýsuvík. What we see is that a lot of the activity is on north-south striking faults. You can see some are longer than others, and some are shorter. But most of the time, we have short, maybe 1 day or 2 days, we have intense activity on a fault, and then it quiets down in between. if you look at the hypocenters, we can see how the depth is distributed. Most of the events are between 1.5 and 5 kilometers. You can see how a majority of the events are in Kristjánsdóttir, and all these faults that we saw on the map before, they are very steep, with close to 90 degrees dip. And which is what we would expect. We know that a lot of the faults out on Reykjanes have this north-south striking direction. Some of them also have a northeast-southwest direction, which we don't see as much or not as clearly in here. What I did was look a little bit closer at the depth distribution. No. Hjalti, do you think this works, the pointer?
Yes, it's not very bright.
No. Yes, okay, I'll just walk over here. You can see how it goes up here. This line shows that around 95% of the activity is above the line. So I divided it into 4 quarters and looked at each quarter by itself. And you can see that clearly the activity is much shallower here. 95% of the events are above depth of around 4 kilometers. What I think this suggests is that the brittle ductile boundary is coming up here in this area, and this is where the Kristjánsdóttir geothermal field is, where most of the activity can be seen on the surface. So these are probably related. What the French group did was to calculate the tomography for the area. So they look at the velocity structure. So we see on the bottom picture, it's the P-wave velocity structure in the area. So blue is high velocity and red is low velocity. And what we would expect is to see velocity increase with depth, but there's a low P-wave anomaly, this red blob here, but it's not what we would necessarily expect to see. But this is what they also found in an earlier study from 2005, which is the reason for why this project was launched. And we also see that there is less activity, seismic activity within the blob. And this is also where we had the uprising in the brittle ductile boundary. The picture on top is the resistivity structure. It results from scientists at ISOR. They calculated the 3-dimensional distribution of resistivity. Here you see that red is low resistivity and blue is high resistivity. And what we see is the low resistivity cap with the high resistivity core. But then we have another blob in here, exactly where the Kristjánsdóttir geothermal field is. So maybe these blobs are related, but they're not at the same depth. In the figure above, we see that the low resistivity anomaly is around 3 kilometers, and it's a lot shallower. The top of the low P-wave anomaly and bottom figure is around 5 kilometers. But they're in the same place, but not the same depth. But what I did was to look at the focal mechanism solutions of all of the events. The focal mechanisms, we used the distribution of the seismic waves to see what kind of a source we're dealing with. So we can then infer what kind of a fault was taking place. Was it a strike slip? Was the fault moving laterally? Or was it a normal faulting event where one side is sliding down, or reverse if it's pushing up? So these are the 3 general types that we have, but many events that we have are sort of a mix. So we have both strike slip and a normal or reverse component. This is one, just an example of one event. So you see this is it's a reverse faulting event because here it's a tensional quarter, but it has it's not just it has an oblique with a strike slip component. It's all very clear. Yes. I had a lot of these balls to play with, and I actually calculated over 1,000 focal mechanisms, but I divided them into according to what their orientation was. So if you look at just a nice little picture of the division, this is for the whole data set. A majority of the events is oblique, with around a fifth as a strike slip and a fifth a reverse, and some normal events. Krýsuvík is pretty similar to the whole data set. There's a lot more events, 900 events. In Fagradalsfjall we have very many reverse events and a fewer normal events, but Fagradalsfjall was a little bit on the outskirts of the seismic network, so that could maybe be not as good data. But we really didn't expect so many reverse faulting events. We would expect strike slip and normal events, but there was very many reverse events. I took Krýsuvík specifically to look at. You can see that these are triangles to show the distribution of what kind of events we have for each swarm. So I divided it into 12 smaller swarms. You can see on top here, this is the whole data, that we had very diverse events. There was a big party for all focal mechanisms. I want to look a little bit closer at one of the swarms, which was in Móholtsadalur going into Núpshlíð. And the black balls shows all of the events. But then I divided them into according to what kind of a source mechanism we had. And a lot of the events were oblique, which is the blue. And then we have a few strike slip events, and then normal and reverse happening. And this is all at the same place at the same time. The swarm took place over 2 days in the end of July, beginning of August. The depth range were about 1 kilometer. So all of these events are there together. It was a little surprising. There's also the strike is quite distinct. The normal events have a very clear strike, while the reverse events are close to 90 degrees perpendicular to the normal faulting. The strike tells you how the fault is oriented for that specific event. But you remember on the map that the big fault that is outlined for all these smaller events is north-south. So we have all these events taking place on smaller structures which line up in a north-south direction. I then took all of these focal mechanisms for these groups, these 12 groups, and I calculated the stress tensor. And the stress tensor for each group can then maybe tell us a little bit about the stress field in the area. And these are very colorful pictures, which is good for me. This is a lower hemisphere projection, so you can imagine that you're looking into a bowl, and these little black symbols, they show the 3 orientations of the stress tensor. So they're all perpendicular to each other. And what we can try to read from this is if one of these 3 symbols is close to the center point, then one of the stress tensor components is pointing upwards. And that's what we want. So this is not, that's what I tried to do by dividing this into little groups to find a stress tensor that actually had one perpendicular component, or up component. So this shows us the stress field, but this shows what the nodal planes that was chosen in the calculation. So from this we can try to read what the direction of the fault is. So there's if it's a grouping here in the chosen nodal planes, it means that we have nodal planes that are oriented northeast, southwest, and they are dipping towards northwest. So we have a lot of faults, or a lot of source faults oriented that way. So this is where the Fagradalsfjall, the area in the west. I took all of the events there and put them all together, and it didn't come out really well enough. But for Krýsuvík, I took these 12 groups that I had and tried to find a stress field that would have one of the symbols closer to the center. It went quite well in most cases, but in general, the smallest stress tensor, the blue, if you try to find that in all of the pictures, you can see that the orientation is close, somewhere northeast, northwest, southeast. Yes? Good. So it's this orientation here, 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 even here and here. It goes. This is a little different, but in most cases, the orientation is quite similar. On the periphery of all the projections, you can see the maximum horizontal stress. So it's taking this stress tensor that we have in here and projected it so we can see what the horizontal component, what's the direction of that. And you can also see that that's in most cases close to northeast, north. And so from that we can, of course, calculate the least compressive stress, which is just 19 degrees from that. And I found in most cases that it's close to 120 degrees to the east from north. So similar to this one here, the blue. And that concurs very well with other studies using GPS or to calculate the direction of which way the plate boundary is moving. Just to show you the different types of nodal planes that were chosen during for each group. We could see 3 types mostly of different nodal planes. These steep north-south, like here or here, and that also has been found on the surface when mapping faults. The longest faults are all north-south striking. Then we have these northeast, southwest as well. We have quite a lot of those, like here, and that's also mapped on the surface. Most of the faults mapped on the surface are oriented this way, but they're a lot shorter than the north-south striking faults. Interestingly, we also have these east-west planes, like here and up here on top. And there are hardly any surface faults that are oriented east-west. So I don't know where they come from. So all in all, there are 10,000 detected events, depth between 1.5 and 4 kilometers. This might indicate an updoming in the brittle ductile boundary, which coincides with a resistivity anomaly and a low P-wave anomaly. And for the focal mechanisms, I found around 1,000 focal mechanisms, and there was a mixed grouping of solutions in all places, but regardless, I found the least compressive stress, which concurs quite well with the least compressive stress from other studies. Thank you.